So really briefly, let's take a look at a set of generalized equations which can help us model rotational mechanical systems. And again, this is for the general case of n degrees of freedom. So general case of n degrees of freedom. And of course, you can scale that down as needed from here. So what that means is, like we've labeled in our other cases, we would have equation 1 up here. This would be equation 2, so on and so forth, all the way down to equation number n, because remember we need n equations for n degrees of freedom. So largely this looks very similar to what we saw for our translational mechanical systems. The main differences now is that instead of talking about a translational displacement, we have an angular displacement. So we have these thetas as opposed to our x's that we had for our our translational mechanical systems. Other than that, it's pretty much the same, and we see the same trends that we saw in our previous mechanical system as well as with our electrical networks. So for example, if we look at this first equation, let's point out some of these trends that we've said before. We notice that if we're looking at equation 1, the only term on the left side of the equation that is not being subtracted is this first term related to theta 1. All other terms have a negative sign in front. Similarly, if we look at equation 2, only the term related to theta 2 is being added all the way down to theta n. So for our nth equation, only the theta n term is positive. A couple other things, of course, if we're in equation 1, we're just summing impedances at 1. For every other term, we're summing impedances between 1 and whatever other point of motion we're talking about. So theta 1 and theta 2, all the way up to theta 1 and theta n be multiplied by n. The only other distinction here is related to the right side of the equation. Instead of our force, which we saw for our translational mechanical system, we now have sum of applied torques. Again, it's applied at our angular displacement position theta 1 as opposed to our x1 we saw previously. And keep in mind too that this is, if we're talking about equation 1 here for instance, this is torque applied directly at theta 1, so not indirectly through some other connections. So we'll see how that works out and get a better feel for how to use these equations in our example in the next video.